All right, so in the interest of time, I think we ought to kick off today's event. So good afternoon. Welcome to the Naval virtual tech demonstration. And today we're focusing on hypersonics and unmanned vehicles. As I said before, I'm Bill Kaiser, the EVP for Science and Technology at IN3. We're the partnership intermediary agreement to Naval Surface Warfare Central Crane for the NAVALX Midwest Tech Bridge. Thanks to all of you for taking time to join this event. And our NAVALX team recognizes that some of you in the audience may think it's something a little different when tech demo is mentioned. But in the short term, this is sort of our primary mechanism for how we're going to be able to meet each other and discuss the technologies that are going to continue to provide technical dominance for our armed forces. Regardless of what you call it, this event is a great opportunity to showcase 5 innovative companies that have technology relevant to Crane and the DoD. We have a diverse audience today of industry, academia, and government with interest in these areas. Now, the primary objective is to initiate discussions amongst this diverse audience that lead to funding and projects that drive these innovative projects to the scientists, engineers, and program managers at Crane. So while this today focuses on Crane, technology into Crane, there are also other opportunities for tech to flow back out of Crane to help companies put their products into the marketplace. So joining me on today's call are Ann Fields, the Regional Director for the Naval Midwest Tech Bridge, and my colleague, Dr. Rod Miller, who is IN3's Chief Technologist in Hypersonics. Rod will lead the section in hypersonics, where we have 3 really good companies. So a few housekeeping rules before we get started. I think we've all been down the virtual path enough, to mute your mute your computers and your devices. That helps keep. So today, of course, is letting companies showcase, but it's also about this exchange and this dialogue. So we want to make sure that we appropriately address questions. We've run a few of these events, and we think what probably works best is put your questions into chat. At the end of the 3 hypersonic talks, we'll rack and stack these questions, answer them all at the end of hypersonics. If some don't get addressed, then we'll type up answers and send them out to all the attendees. I want to make sure we stay on schedule. I think that's really important, particularly whenever we have sort of these diverse audiences. Some may want to concentrate on hypersonics, and some may want to concentrate on UAVs. It's going to try to make sure we keep on track. So with no further ado, I'm going to kick this over to Ann Fields. She is the Regional Director for the NAVALX Midwest Tech Bridge. She's going to talk to you a little bit more about what Tech Bridge is and why it's really important and why there's so much excitement about it in Indiana. So over to you, Ann.
Thanks, Bill. Very much appreciate it. Welcome, everyone. Thank you so much for joining today. This is our 2nd technology demonstration that we've done with the Midwest Tech Bridge. And to kind of back to Bill's point, it's definitely been a learning experience. We had our first one on March 31st, and we've learned a lot since then. So really excited about the opportunity today to learn about some of the technologies within our innovation ecosystem. So just as an overview, we have a new CEO at Crane, Captain Duncan McKay, and Dr. Kyle Warner is our current acting technical director. Next slide, please, Derek. So I think a lot of you guys on the call have seen my presentation before, but I do want to hit just a couple of the high points for those folks who haven't had the opportunity to see the presentation yet. So to understand the Midwest Tech Bridge, one must first understand what NAVALX is all about. And NAVALX's goal is really to be a super connector and focus on scaling non-traditional agility methods across the Department of the Navy. And they do that in a couple different ways. The main ways are the 4 listed at the bottom here: launch platforms, awards and stories, and playbooks. All of that work really comes out of the Alexandria, Virginia office. That office is staffed rotationally by different folks from the warfare centers. They really focus on lots of different training events, human-centered design type events. They really communicate in a non-traditional way. Lots of, go lives on LinkedIn, and just a really non-traditional way that what we've seen public affairs officials speak previously and kind of go public previously. And then finally, playbooks is really focused upon capturing best practices, maintaining them, and then sharing them with the user community. So the idea of NAVALX the idea of the tech bridges is that really Naval X couldn't be successful only within the Beltway there in Alexandria. And so they wanted to have sort of outposts as the tech bridges. And so really proud to say that the Midwest Tech Bridge was one of the first to be put into action. Derek, if you could go to the next slide. The spaces in red here are the first 6 tech bridges. They've had 6 more come online since then. And as a fun note, there will be more coming online to include ones that are OCONUS. So some really interesting things about these connections is that we have weekly syncs with the directors of all of these locations. And now that we're all stood up and really kind of all going in the same direction, there's been a lot of conversation about potentially having events between some of the tech bridges. So, you know, potentially sharing what the Midwest is doing with the 401 tech bridge per se. So really excited about opportunities that can arise amongst these tech bridges. And one thing I want to note here too is if you look at this presentation, you could infer that the tech bridges are focused regionally, and they are, but it doesn't mean they're exclusively focused regionally. So each tech bridge has some focus areas. We'll talk about ours here shortly. But if there's technology in Southern Florida that relates to what the Midwest Tech Bridge is doing, we certainly want to hear about that. So we've had a lot of engagement in our last event. We had about 20 different states represented for our small business presentation. So really exciting how this is kind of growing and developing and bringing those connections together, because that really is our goal, is to hook problem owners up with solution providers. Derek, next slide, please. So these are the 10 focus areas that we have currently for the Midwest Tech Bridge. So like I mentioned, other tech bridges have them as well, but these are really the things that align with Crane's mission areas. And so we're really most interested in this type of technology from the folks in our ecosystem. That doesn't mean that we aren't interested in talking with other folks. We've talked with folks in the medical world, in the textile world, and are happy to vector them in the appropriate direction. But Crane specifically, this is where we're focused. Next slide, please. So these are the 4 Midwest Tech Bridge success factors. And we'll talk through some more in detail than others, but the first goal there is really to expand and engage the internal and external network. So that really comes into play today for this technology demonstration. The internal network is the Crane team. So the SMEs, the chief scientists, chief engineers, those folks within Crane who are the problem owners. So we have what we're calling the Midwest Tech Bridge Steering Group. And that group broken down by the focus areas that we had on the previous slide, to where when an organization who perhaps specializes in hypersonics gives us a capabilities presentation, or we somehow come in contact with them, it's a way for us to quickly vector that information to that internal team. So obviously without that internal engagement, the Midwest Tech Bridge would not be successful, because we really need those problem owners engaged with what's going on to see what in the ecosystem can help them solve their problem. That external network, we really rely very heavily on our partnership intermediary, Bill Kaiser and team at Indiana Innovation Institute. So we leverage their network, and we've actually been building upon that network as we've been in business since about March of this year is when I came on. So we're building upon that network, and we really have a lot of our communication funneled through IM3 as our partnership intermediary. The next bullet, we can talk more about this if anyone has questions on the side, but that's each tech bridge is charged with having a collaboration space. The goal is there to have a low barrier to entry space where folks can come in and collaborate. In the post-COVID environment, we're hoping that we'll be able to do events such as these in our collaboration space. We're actually looking, and actually IN3 is spearheading this effort, having a cyber physical systems innovation and collaboration space at Westgate, hopefully in the next few months. I'm actually let's go to the next one, championing the Naval X innovation pipeline. And then one more slide, please, Derek. If you wouldn't mind playing that. Thank you.
For entrepreneurs, startups, and small businesses, it can be tough to partner with large organizations. It takes vast personal networks, years of experience, and oftentimes some luck to get your product delivered. That's why we created NavalX Tech Bridges to help get your ideas and technology directly to those in the Navy and Marine Corps who need it, fast. Our Tech Bridge network is deeply embedded with sailors, Marines, academia, and innovators in the private sector. That means we are uniquely positioned to connect problem owners with solution providers and to drive their products where they need to go. We've mapped our vast network of naval programs across the innovation pipeline, so you always know where you are, where you need to go, and who will help get you there. That way, you can better manage your resources and chart the most effective course to delivering your product. For more information, visit our website and let us know what you need. Your next opportunity is closer than you think.
Thanks, Derek. So as you guys can see, that video is really focused on our external ecosystem, trying to help folks understand where they are at in the process of doing business with the Department of the Navy, Department of Defense, and trying to get them in touch with the right people. So this event is actually one of those ways we are hoping to try to make some sort of intentional connections. Next slide, please. So our final focus area is a widely communicated and targeted calendar of events. So that calendar of events is really what we just talked about, is an intentional way of linking people up. So small business events are really focused on the external ecosystem, helping folks, small businesses, innovators, startups, industry, academia, helping them understand how to do business with the government. We've had quite a few of those events. If you guys haven't seen them, please check them out on the NavalX webpage under events, or on our LinkedIn page, as well as IN3's page. We discussed briefly the technology demonstration and the idea there, but the idea of the technology demonstration is to have the solution providers, so the folks that you'll hear from here in a little bit, present their capabilities and their solutions to the problem owners. So those are the internal, so the external ecosystem presenting to the internal ecosystem. And one thing I want to note here too is I wouldn't at all be deterred by not a number that we wanted to see in participation here, because all of these events are videoed and shared very widely. So I know of a couple people at Crane who weren't able to participate today, but I very much intend on sharing this video with them afterwards to get the widest dissemination. Technology showcases are really focused on technology transfer, so tech out of Crane, and we haven't delved too far into them yet, but we will in the coming year. And finally, innovation challenges are where the problem owners share their problems in a distribution A format with the potential solution owners, with the hopes of with that intentional collision with linking them up. I hope that makes sense. So yeah, so again, all of these are recorded. We try to share them as widely as we can, so folks have them for reference material well into the future. Next slide, please. So that really links or culminates my my comments for today. One note that I just wanted to put out there is that we do have Annie Bullock online as well. She is acting for our technology transfer director, Jenna Dix. So if anybody online has any T2 related questions, feel free to add them to the chat, and Annie will get to them when we take the Q&A. Also, if you guys have any questions of us, I'm Ann Fields, my email is on this slide, and my deputy is Julie Schaff, and she's awesome. So feel free to reach out to either one of us, and I appreciate everyone's time being here today and look forward to what all the presenters have to say. Thanks so much, guys.
All right, thank you, Ann. And to everybody online, we're really fortunate to have such a strong forward-looking Navy team. It makes all the difference, and I think the Midwest Tech Bridge is doing extremely well, and it's going to expand out to the other tech bridges and continue this sort of collaboration. It's really important to IN3 because when IN3 was founded 3 years ago, it was really about working with academia, industry, and government to be able to create a hub of national security for the Indiana region. So what does that mean? I mean, that means that we look for capabilities inside the universities and the small companies. We look at our we look at our customers' needs, and we try to put together programs and activities that bring that critical mass forward into innovation. Certainly one of those areas where we had started our focus was in hypersonics, great universities, great small companies, and a need inside the government. So we made an investment in hypersonics at IN3, and we're fortunate enough to bring home a fellow Hoosier back to Indiana to lead this effort for us, Dr. Rod Miller, PhD from Purdue, retired Air Force colonel, former chief scientist at Global Strike Command, extremely deep pedigree, deep network, is leading that activity for us. So he's going to lead this section today on hypersonics. So over to you, Rod, to talk about these 3 innovative companies working in hypersonics related technologies.
All right. Well, hey, thanks, Bill. I appreciate the introduction. I'm very excited to introduce these companies to those who are listening. And they're just a sampling of the great work directly related to hypersonics happening right here in the state of Indiana. It's my pleasure to have, for the first round, Dr. Tom Grunwald, the COO of Blue Wave Artificial Intelligence Labs, and Dr. Carlos Scalo, the CEO and founder of Hysonic Technologies, LLC. They're both from West Lafayette, Indiana, and you'll find that that is a theme for this particular group of folks. They all represent the Purdue ecosystem. That's more of an accident than on purpose, but certainly reflective of what's going on up here in the West Lafayette area. Tom Grunwald is a very accomplished technology leader, having been the former Tel Labs Chief Technology Officer, Westel CEO, and Bell Labs executive. He's also a Purdue alumni, having received his master's and doctorate at Purdue in theoretical physics. So he pretty much knows everything. In addition to his leadership at Hysonic, Carlos Scalo is associate professor in the School of Mechanical Engineering, as well as Aeronautical and Astronautical Engineering by courtesy at Purdue. He completed his postdoctoral appointment at Stanford, his PhD at Queen's University in Canada, and his bachelor's of engineering and his master's of science of engineering in aeronautical and astronautical engineering from Naples, Italy. Carlo has been recognized multiple times by the DoD, receiving 3 distinct Young Investigator Program awards. So that puts him in pretty high regard amongst our DoD partners. Tom and Carlo will talk about their predictive modeling framework based on a combination of artificial intelligence and computational fluid dynamics for aerodynamic optimization of hypersonic glide bodies. Tom and Carlo, over to you.
Thank you, Rod, for the introduction. Carlos Scalo here. I'm representing Hysonic Technologies. I hope you guys can hear me well. And it's a pleasure to deliver this pitch together with Tom, who's representing Blue Wave AI Labs. So we're going to talk about glide bodies and how machine learning can help us design the aerodynamic shape of these glide bodies. And you're seeing a stock photo of something that looks like a hypersonic vehicle on the left here. Next slide. So we are in the middle of something that is essentially a Cold War, once again. They call it the Cool War right now. And it's an arms race between the United States, Russia, and China. And it's a race that is being played at all levels, from fundamental research. There's a battle as to who's publishing more, which is a little strange, and we can talk more about that later. And there's a battle, obviously, in who's developing classified, the restricted technology, the fastest, and who can show the capabilities, specifically when it comes to developing hypersonic missiles. Hypersonic missiles are missiles that travel so fast that they're very hard to stop, and they would give no warnings at all. They would give no chance for your opponent to react to them. So next slide. China in a National Day parade, this was October 1st, I believe, 2019, displayed a lot of weapons. One of them was this DF-17. If you see, it is a missile, and the shape is meant to imply it looks like a hypersonic vehicle. It looks like a hypersonic missile. Obviously, we don't know much about it, but all that we know is that the Chinese government made the statement, tried to make the statement to the world, saying, hey, we have this technology ready, and we could fire this missile anytime. Next slide. Russia is in the same, the Russians have actually been working in hypersonics longer than the Chinese, at least according to public literature. There's a lot of well-respected scientists in Russia that have been working in hypersonics. Many of them are banned from the States right now. And they claim they have their own hypersonic weapon that can travel all the way up to Mach 20. Next slide. Why are hypersonic weapons a big deal? Well, if you take a look at this chart, this is sometimes also called the hypersonic pizza delivery chart, or slide. What you can see is you have these 4 trajectories, and they show you what you can do in 30 minutes. Well, if you want to deliver a pizza from Washington, D.C. to Wichita, Memphis, or Cleveland, well, you have those options there, and you see at the bottom, you see what the aircrafts that would deliver this pizza look like. But hey, if you want to deliver the same pizza in Micronesia, which is 1,300 miles away, 13,000 miles away, and you want to do it in 30 minutes, you need to design a vehicle that looks like that red arrow that you see at the bottom left. The details of that little dart are obviously pixelized in the slides, but I can guarantee you that the aero shell, the body of that vehicle, are engineered to an extent that is meant to make them survive this flight. 30 minutes covering that much distance, it means that you're flying in a ball of fire. Next slide. The physics are very complicated. What you see on the right is not that specific vehicle that you saw earlier. This is a simple cone. Simple, you can think of it as a dart, but shaped as a cone. Simple geometry, but as you can see by these simulations, this cone travels in a shock wave. That shock wave has a particular shape, and that can only be predicted with accurate computational fluid dynamics, which is what Hysonic technology brings to the table. So we bring traditional and well-established knowledge of the fundamental physics. But this process is very expensive, as Tom will mention, will cover soon. So Tom, you can, I think this is your turn now, and we can move to the next slide.
Tom, you're on mute.
Yeah.
My apologies. I was overly considerate. Anyway, it's interesting to see the new innovations in the use of AI, and one of the leading areas where this has been done has been the development of prescription drugs. As everybody knows, that's a very long, arduous trial and error process, and people have recently figured out how to use AI to short circuit that process and not have to look at so many different alternatives and then restart when things are done. This is much like if you're familiar with the fact that there's been a program called AlphaGo, which has beaten the top Go players in the world. The outcome of that not only was the fact that it was able to defeat expert humans, but it also developed strategies that humans had never considered, and they were winning strategies. And the same is starting to be true in the drug area, where folks are seeing drug combinations that no one would have come upon on their own. Next slide. So taking a page from the drug area and understanding how they've used AI to develop new and innovative drugs in a very, very short amount of time. And as you saw on the slide before, 46 days instead of a few years. We've had a joint effort between who not only brings the expertise on hypersonic flow physics, but has an extensive capability to do simulation models. And he's experienced in this area, having worked for quite a while with the DoD on some of these projects. And so Carlo's area is to provide data basically for the artificial intelligence to use to try to figure out what the next best design is. And on our side, we've been applying AI to advanced science and engineering problems for some time. Most of our team is, have advanced degrees in either engineering or science, or in some cases AI. So we tend to understand the areas that we're working in. We've done a lot of work with nuclear power generating reactors, safety relief valves, and also analysis of war games in a project called Game Breaker. Next slide. This slide is very interesting, and it's at the crux of why AI is important in hypersonic design. If you look at the picture on the bottom before we get into the details of the process, you see a gray line which represents the shock wave. And then underneath, so we're looking at a side view of a cone. Underneath that, you see a dark black line, which as it goes to the right, becomes suddenly more involved in detail. That particular line is an it's an isosurface of the fluid gradient, of a fluid density gradient. And so the simulation that looks at this is able to ferret out all that kind of detail. Then underneath that, what you see are these blue warms. Those are isosurfaces of velocity invariance, and the color is indicative of the temperature, because after all, what we're trying to do is understand the turbulent surface heating of this vehicle as it goes hypersonic. And this is a Mach 7.4 simulation. Now, why is this important in the realm of AI, and how can AI help this process? Well, just this particular diagram took 1 month of high performance computer time, supercomputer time, and you can only imagine how many dollars that costs. So this process is extremely important. It's extremely expensive, and it also generated over 2 terabytes of data. So there's a lot more to this picture than just a few pretty colors. This tells a big story, but it's only telling the story for one particular design at one point. So the process that Carlo's team and my team have been working with has been to design 2D aerodynamic shapes. So Carlo's team does a simulation of a set of aerodynamic shapes with different parameters. We're also going to extend that to 3D and then real applications. Then those are put into a machine learning program which learns the design. It learns how the design is related to certain parameters like heating, the fluid density in certain areas, et cetera. And then after that, we can put in desired parameters, and the machine learning program will tell us what are the specific aspects of that design. Next slide. So this is just a quick picture of a particular design that then is used to generate a surface, a solution surface, which might be drag, it might be surface temperature, it might be a combination of those variables. And this is the output of the machine learning program, where it can put out a whole spectrum of shapes and with design parameters. And then we can then find out where on that surface are the areas that we're interested in. Next, please. This is perhaps a little better view of how we use it. So once we've developed a surface that relates the desired parameters to the design specs of a particular, we can use techniques like gradient descent to find optimal characteristics like optimal heat transfer, optimal drag, etc. And that's really, in a sense, in a nutshell, how the design process goes. We start with simulations from the hypersonic experts. We feed those simulations into a machine learning program. Out of that program, we're able to construct a surface of various design parameters and then optimize the parameters that we're interested in. Next slide. This is then how we intend to evolve the process. You can start, like we said, with a simple 2D design. We take that to 3D, and then finally we go to very complex designs that are indicative of real world problems and real world situations. Next. Another application of this, since we have the ability to generate like we said, designs very quickly that are based on specific environmental conditions, you can imagine doing the design, the AI-based design for various parts of the glide path, the initial, the unpowered phase, and then the maneuver phase and the dive phase. And in each phase, we would get a set of optimal designs for the particular shape. And in that way, we could potentially recommend certain shape changes that would further enhance the optimal performance of a hypersonic design or a hypersonic vehicle. Next. So with that, that concludes the part of the presentation where we talk about the design process and how the capabilities of generating a lot of different simulations allows us to feed and inform a machine learning program that will then be able to generate new designs. But I'd like to talk very quickly about some of the things that our company does. Next slide. We're located near Purdue University, and one of the many companies down here that are closely associated with the university. And one of our biggest assets is, one, we have access, of course, to some of the biggest experts in the world, whether it's in engineering, as we've partnered with Carlo, or whether it's in computer science. And we're able also to hire some of the best students in the world. And so what are some of the projects that we've done? Well, we've done some adversarial environments for conflict trained agents. That's a technique called reinforcement learning, and we've used that technique to train bots to fly Air Force fighters. We've also used some of these techniques to do fuel optimization for nuclear power plants. We've also used something called natural language processing to document classification. So we look at trouble reports from the NRC and try to predict where will the next problems be in a particular reactor. Also, machine learning's been used to do analysis of video and satellite images to extract information from those images and do predictions based on that. And then, as I pointed out before, we've done game strategic AI analysis of war games. Next. This is a quick overview of the company. I won't dwell on this, but the middle part of this, where we talk about the capabilities, is interesting. The good news about AI is it's really fast changing, and new techniques are coming along all the time. The bad news is there's a lot to learn, but it's a really great industry and a really great area. And it really has expanded recently the number of problems that can be attacked with these techniques. Next. Next slide, please. These are some of the current projects. I won't go through these in the interest of time, but you can certainly read them. One of the more interesting ones in the nuclear reactor area has been the moisture carryover problem. Reactors don't like a lot of moisture in there, and often the power company have to shut down if too much moisture comes in. Now we've been able to generate an artificial intelligence informed model that helps them know whether they really need to shut down or not.
Hey, Tom, I'm sorry to interrupt you. We need to go ahead and wrap this up.
So I'm finished right now, and I'll turn it over to Carlo.
All right, we really got to get going. Thank you.
Go ahead, Carlo.
Yeah, I have 2 slides. I can do them in less than a minute. Next slide. This is just an overview of what we're doing now. I don't see the next slide coming up. Maybe it's me. Yes, that one. And so we have been funded by ONR, the Office of Naval Research, to design aeroshell for glide bodies, and specifically to manipulate the hypersonic boundary layer that evolves over this aeroshell. This is as much as I can say publicly, but if you want more details, you can talk to me. And we were able to passively control the structure of the hypersonic boundary layer to enable faster flight, to reduce the aerodynamic drag. Next slide. And we do so by leveraging also the hypersonic wind tunnel facilities that we have at Purdue, which are top class. And this is a very simple Mach 6 flow, very simple for Purdue to measure, and that's a test model that we have created and manufactured, and that is being tested at Purdue. This is very fundamental research, but if you want to know more, please contact me directly, and we can talk. I can share more information in that case. Thank you.
All right. Hey, thanks, Tom. Thanks, Carlo. A great presentation, highly relevant to the whole concerns of hypersonic system development. So I hope that there will be some great questions for you after we're done with this this block. Next, we have David Beering, who's the principal owner of Intelligence Designs, also in West Lafayette. David earned his bachelor's and master's degree from Purdue. During his career, he's held leading roles in more than 85 projects, working with organizations across the DoD and the Defense and Industrial Base. He's here to talk about his company and how it's developing advanced communication techniques as well as modeling simulation to facilitate radio frequency communication through plasma fields based on experience with previous government applied research efforts. So David, over to you.
Thanks very much, Rod. Can you hear me okay?
I hear you loud and clear. Maybe
Awesome.
you might turn your volume up a little bit.
Okay, will do. So this is how you can reach me if anyone has an interest to follow up with me afterwards. Derek, if you could go to the next slide. So I'll start my presentation with just a little bit about my company. It is a very small business based at the research park just north of Purdue's campus in West Lafayette. I was based in the west suburban Chicago area for 30 years. And during that time, did a lot of work supporting various initiatives in high performance computing, networking, and satellite communications. As Rod mentioned, some 85 different projects involving satellite communication systems and high performance line of sight systems for a variety of different platforms, including ships, aircraft, land mobile vehicles, and spacecraft. We have the privilege to hold a prime contract with the U.S. Naval Research Laboratory in Washington, and also have active contracts with Sandia National Laboratories in Albuquerque. Next slide, please. So, so this is a little bit different spin on hypersonics because I'm going to spend very little time talking directly to the hypersonics topic, but I'm going to talk around the topic and talk a little bit of inspiration. So there were three projects in my recent portfolio that caused me to be interested in hypersonics. The first was a program that we performed alongside Sandia National Laboratories for the Missile Defense Agency called Directed Satellite Telemetry. That involved connecting a satellite link from an exoatmospheric vehicle, a test vehicle, in the MDA's target portfolio to the ground via geostationary satellite to deliver real-time telemetry. I'll talk a little bit more about each one of these. The second project is one that's currently active, is the development of a from-scratch Ka-band satellite communications terminal to operate on a stratospheric balloon platform. And those platforms typically operate between 55,000 and 85,000 feet above sea level. That is being performed in partnership with the U.S. Naval Research Laboratory. The third one is a piloted airborne satellite communication system that was developed also with the Naval Research Laboratory and SAIC at the time, just right as they were transitioning into Leidos. And it involved the from scratch design, integration, testing, and certification of an X-band satellite communications terminal for a piloted aircraft. Next, please. So first, the program for the Missile Defense Agency with Sandia. This system utilized NASA's tracking and data relay satellite system. One of the first things to consider in a large system like this is the choice of satellite systems. Not only GEO versus medium Earth orbit versus low Earth orbit, but also what frequency bands to operate and what satellites are available in what orbital slots, et cetera. So there's a lot of geometry involved, and we selected a system that's operated by NASA that at the time was supporting the space shuttle, currently supports the space station and the Hubble Space Telescope, among other assets. We built a unidirectional IP data link. This was one of the first times that a high-speed S-band data link at IP had ever been built over TDRS, as it turns out. And that operated between the payload deployment module. So as soon as that vehicle went exo-atmospheric, the payload deployment module deployed the reentry vehicle, and our satellite terminal unfurled and created a 2 megabit link to the ground via the satellite. During 2 successive flights, we performed that test and delivered each time more than 500 megabytes of pristine data from space. This is the first time that they had ever had a data set of this quality that had ever been delivered, because most of the time these assets use direct-to-ground links, and those links are very, very unreliable and very high in bit error rate. So next slide, please. This is our current project. It's again designed for long duration operations, so up to a month or 2 at a time from a balloon gondola at 55,000 to 85,000 feet MSL. It's designed to operate on either military or commercial Ka-band geostationary satellites. We're also considering some medium Earth orbit satellite options. The aperture is 60 centimeters, so it's a fairly small, compact system. The objective power draw is 100 watts continuous. The objective weight is less than 50 pounds. We're looking for 10 megabits off the platform and 2 megabits back. This is rather revolutionary when you consider that most of these platforms are running data links in the kilobits per second. And size, weight, and power, of course, are gigantic drivers in a system like this. Next, please. So this is a picture that was taken in at Bagram Air Base in Afghanistan. This is a Dash 8 aircraft, and this is an airborne satellite terminal that we literally took from PowerPoint charts to operation in theater in about 12 months. It's based on a 0.4 meter aperture that at the time was manufactured by EMS Technologies. Again, a lot of work goes into the selection of the components and the various technologies that need to be integrated to make something like this function. The objective transmit data rate, which was met, was 10 megabits per second off the aircraft using an X-band geostationary satellite. The objective received data rate back to the aircraft was 2 megabits. That was also achieved. As you can imagine, with the piloted aircraft, since we're supporting human lives on the aircraft, not just a UAV, but now we've got a whole lot of additional safety protocols and certifications, and the RF systems have a whole new level of scrutiny involved. And as I mentioned, we had less than a year to take the system from a PowerPoint chart to an operational system in CENTCOM AO. The next chart depicts where we did our initial integration of the system. This is a hangar at Ali Salim Air Base in Kuwait. And the reason I mentioned this is that we committed an act that was unthinkable at the time, and actually I'd probably not select or elect to do it again. We did our initial integration of a very complex system that had never been fielded, and we did that 8,000 miles from our logistics chain. So as you can imagine, anything that you need, you can't go down to the corner store and buy it. So we were literally at the mercy of FedEx and other logistics to make this happen. It was quite involved, quite stressful, but a great experience and a wonderful success at the end. Next slide, please. So all of these programs, and the reason I mentioned them, there are a whole host of other programs that I worked with the Missile Defense Agency about 10 years ago that focused specifically on modeling a simulation of communication systems and airborne vehicles of various types, but mainly targets and interceptors in the MDA parlance. But looking at building communication systems specifically to support that unique environment. Size, weight, and power drive everything in this game, and oftentimes budget becomes an additional factor. But fortunately, in our airborne piloted program, the sponsor took budget off the table as a constraint. So we had the luxury of being able to go real fast, and budget often makes that possible. All these systems operate in a very unique environment. All those environments are extreme in their depending on their peer systems. Due to the unique environments, all of these projects are very multidisciplinary, and you'll see here in the next slide that we talk about some of the unique disciplines that are going to be involved to build communication systems that deliver reliable communications for hypersonic vehicles. But all these systems have a requirement for deep expertise in a lot of different disciplines: RF, mechanical, materials, shock and vibe, extreme temperature variations, and it goes on from there. Developing the communication systems to operate reliably on hypersonic vehicles will absolutely require this same type of multidisciplinary approach. So next slide, please. So looking at hypersonics specifically, so finally I'm going to get there. We're working to determine the best way to establish reliable communication links from hypersonic vehicles to satellites or directly to the ground through plasma. And one of the biggest challenges for these vehicles is you've got some really unique shapes. You don't want to interfere with the shapes of the vehicles because that enables their ability to fly through the environment so quickly. But in order to enable communications, you have to open up some ability to communicate from the vehicle. So one of the things that we're working on is trying to determine the best way to actually use the plasma to our advantage. Can we modulate through it? Can we modulate it and make the plasma behave as an antenna? Work is just getting started, and I always get a kick out of there's a group of us that get together here in West Lafayette a couple times a month, and they're some of the two previous speakers and Rod are part of that group, and I'm the guy who's always sitting in the corner drawing on the napkin trying to figure out how to build it. So we're working with some amazing folks. The Naval Research Laboratory is definitely part of that conversation. Purdue's School of Aero and Astro, Purdue School of Electrical and Computer Engineering, and Carlo and Tom are also involved in that conversation. We're just now in the process of starting to put some more structure behind the whole concept, and that's all going to be hopefully taking form in the next few months. So final slide. So why Purdue and why now? Well, Purdue has expertise in a lot of disciplines that are going to be needed to characterize the problem, assess the options, perform modeling and simulation to verify the science, and test and implement the eventual solutions. So it's not just a human capital thing. Purdue has two unique laboratory assets that are going to aid in the evaluation of the communication system options, and both are coming online very soon. The Mach 8 quiet wind tunnel, Carlo also mentioned the Mach 6 tunnel, and also a high pulse shock expansion tunnel. So that's going to allow us to do certain tests at the right temperature, not just at the right speed. So it's a really key feature. So our goal is to perform the systems engineering and integrate the communication systems challenges into the conversation before the concrete dries, so before the design's complete. And my experience over 30 years of working in communication systems says that these systems are often an afterthought. So our hope is that we can design the communication systems into the vehicle ahead of time, as opposed to attempting to snap them on later, which might not work very well. And I think that's it for me. Thanks
so much, David. And this is fascinating stuff, highly relevant, obviously. just the ability to communicate with these types of systems is a key feature to get the data. As most people on this conversation know, going out to a range to do flight testing is extremely expensive. And if you do not get all the data that you need to get, then you have to go back out and do it again, and it just costs a lot of money. So you're enabling not only that capability, but of course, potentially the warfighter to be able to do what they dream to do with hypersonic weapons, which is to retarget them mid-flight. And your technologies might help to solve that problem. So thank you. So finally, in this block of hypersonics, we have BJ Austin, who's the president of InSpace LLC, again in West Lafayette. BJ became the co-founder of InSpace LLC in 2003 after earning his master's degree in aero and astro engineering here at Purdue. As a president, he leads the company's research into technology to solve challenging problems in aerospace propulsion and directs the company's analysis, modeling, and data collection work in support of customer programs. He's going to talk about pressure gain combustion achieved through the use of continuous detonation wave engines, and offers one of the few paths available to significantly increase the performance of aerospace propulsion systems. InSpace is currently working to advance this technology. BJ, over to you.
Thanks a lot, Rod. Next slide, please. We're not a new company. I guess we shed the startup label some time ago, but we are still small. We haven't had a whole lot of engagement with Crane over our 17 years of business. So I thought it would be good to put together a little bit about us. We are aerospace propulsion experts. And principally, we want to make aerospace propulsion systems better and cheaper and safer. And so we've been focusing on that from the standpoint of conducting a lot of research and development. That's how we got our start, and then that grew kind of naturally into engineering services that we spend about half of our time performing, and then out of that grew, and our R&D grew a few products that have gotten use in the lab and around the country. There are just 8 of us. 6 of us have advanced degrees. We do have a very capable technician who's been working in aerospace for 20 years, and David mentioned about having an 8,000-mile supply chain, logistics chain. I get nervous when he goes out of town, to be honest. Everybody's very crucial here. Lots of hats are worn. You can see some of our customers there. Of course, the ones that I can't talk about in an open forum are in the prime contractor arena. We do get to work on some really neat stuff for several different companies trying to make what they do better. So let's go to the next slide on our R&D. And again, just wanted to touch on some of this. So liquid propulsion research was really where we got our start. And this is focused on not necessarily trying to beat an RD-180 rocket engine in performance, but looking at different solutions in order to make the systems more usable and a lower cost and achieve capabilities that otherwise were not present. And one of our first projects in that upper picture, that was for the Missile Defense Agency, trying to create a liquid target vehicle. It's hard to get the foreign adversaries to let you conduct tests against their missiles. So this was trying to replace a Scud or intermediate range intercontinental missile, and they were using a component that was fairly heavy, fairly expensive, and required a lot of art in addition to into science to make. So we looked at a different way to make that work. That's just one example. About 15 years ago, NASA was interested in using liquid oxygen, liquid methane as propellants on board what was then the Crew Exploration Vehicle, and really injectors hadn't been developed for deep space use of those propellants, where they might sit you might need to run them for minutes, or you might need to run them once every day. So we worked on injectors for along those lines. And then another area was really combustion stability work, where that's the main technological risk in developing new propulsion systems. And so we were working on technologies and with other high fidelity modeling houses to develop solutions there. We did get into solid and hybrid propellant formulations, really not so much in the design of the motors themselves, but how to make better fuel grains for these. And one of the things that you kind of start down one path and you go a different way. We were working on a munition that was insensitive to shock and impact. And while we saw some benefit there, what we really saw was that it burned really quick. And so from that, we developed what we call the digital divert attitude control thruster. So you have several of these. The lower image there is a solid motor that reaches 25,000 psi and burns about a pound of propellant in 3 milliseconds. So really neat, a neat outgrowth of that technology that we didn't expect at the time. Another area was working to improve safety. Of course, when you have propulsion systems, that's a lot of energy density, and we were looking to improve the safety for soldiers and sailors around missile interceptors, and within the SBIR program. And we initially tried to do a propulsive solution there, but then it occurred to us, well, we're not probably going to solve that particular problem that's plagued the industry for 50 years in a phase 1 and phase 2. So we went another route and looked at vapor containing foams. Really neat, very, very highly successful technology there. We were able to contain the vapors of hydrazine for 3 days with a single foam application, which is important if you look to put liquid missile interceptors on board Navy ships. Let's go to the next slide. Just a bit on our engineering services. So I mentioned the testing support. We've been doing that fairly significantly for about 4 years now, working on different propulsion systems for vehicles that are headed to space here in the not too distant future. All of our testing experience has led us to be able to offer that as a service to other institutions, and of course, being right next to Zucro has its advantages as well. We've done a lot of parametric analyses. People will often say, okay, we're looking to do design trade space here. Can you please run these scenarios? We got to start actually doing this for a missile interceptor that became the kinetic energy interceptor for the Navy, an MDA. We build a lot of hardware and we design a lot of facilities. The lower left image there is an 8,000 gallon per minute flow facility or a test stand that we built for a customer. That was a really neat project. Pretty satisfying to see that water tank fill up very quickly. Okay, so I'll skip over the products. We'll just go to pressure gain combustion on the next slide. So I wanted to introduce, and let's go ahead and go to the following slide after that. Pressure gain combustion might be fairly new to you. Most of our experience in our everyday life is with deflagration combustion. So it's a candle burning, that's your jet engine, that's most of your rocket engines. It is, we say it's a relatively slow process, even if your combustion, even if the propellants are in the rocket chamber only in there for 3 or 4 milliseconds. So deflagration is a relatively slow burning, smooth process, subsonic. Where we're working now with pressure gain is utilizing the detonation of propellants, or supersonic combustion of propellants in order to achieve more energy. So the upper left graph there has, you can see the 2 different cycles there, and the additional energy that is, the additional thermodynamic work that is available through detonative combustion through the Humphrey cycle is about 15% more than with the Brayton cycle and constant pressure cycle. So really very, very useful amount of energy that if you can make it work. is available for you to use. So in the upper right image, this is flows from the bottom to the top. Sorry, I prefer it going the other way, but this is what we had available. So propellants will enter into an annular chamber, and when you start an ignition and you're able to confine that heat release, you can achieve a detonation wave that traverses radially around, or azimuthally around the combustion chamber. The benefit here is that you can work on a much shorter time scale and a much shorter length scale in order to convert your propellants, your reactants into products. The advantages are high pressure ratios and high temperatures. Those are also challenges to overcome. There's another, so that's the rotating detonation prospect. There is a pulse detonation technology that's been looked at. That goes back to about starting in the early 90s. You may have seen this. This is where you inject propellants into a long tube that is then ignited, and you have a deflagration to detonation transition that then expels the products at a high velocity. That technology has been looked at for about 20 years, and they actually put together an engine that ran on that for flight. But it does have a lot of limitations, mostly with valving, and there needs to be a purge cycle that occurs. Okay, let's go on to the next slide. I'm going to talk a little bit more about. So I'm a rockets guy. We are bringing Dr. Carson Slaybaugh in to the company for the air breathing aspects. But let's go to the following slide. So looking at applying this rotating detonation engine to a rocket, we set about doing a sizing analysis to see if there were actually system level benefits, and what the technological challenges are. The good news is that and then a sizing analysis, and this was funded by a couple of U.S. Air Force Phase 1 SBIRs, we do get a significant benefit. So as you can see there in the upper right, we do see several percentage increase for a number of propellant combinations in specific impulse, which is thrust divided by your mass flow rate. So you're able to achieve more thrust for the propellants you're carrying, and even going into the liquid phase where you have both liquid oxidizer and liquid fuel, then your benefits really start to get up into the 12-15% range. And I should say that 4 or 5% may not seem like a terribly significant performance advantage, but when you consider the fact that deflagration combustion is at pretty much its peak, we're to the point where we can't really squeeze any more energy out of those materials without going to design things that are different commodities, or going to higher and higher pressures, which have a lot of design challenges. Your vehicle gets heavier. So being able to replace the engine with something that is on the same scale of what you're currently flying and achieve this benefit, a 3%, 4% increase in ISP would be tremendous. You'd be able to put up 8%, 9% more payload to low Earth orbit. And currently, NASA and the Air Force are working at trying to improve in tenths of a percent of ISP, and contributing a lot of resources there. So if we can get even half the percent of these performance gains, would be quite something. There are a number of challenges to this, though. The pressure ratios that we see are very significant. We're talking on the order of 400 psi, 400 times the pressure of the reactants is the peak detonation pressure wave, and associated very high temperatures. So we have a very challenging environment in which to operate, and trying to get a sustainable wall in addition to trying to inject the propellants in these scenarios. And then how do we build a nozzle that effectively captures the exhaust of this spinning detonation wave? If we go to slide 9, this is our current phase 2. We just started 6 months ago, and we've achieved some notable operation thus far. So this is operating on liquid oxygen and gaseous methane propellants, and it's designed to operate up to 13 pounds per second of total flow, which is about 5,000 pounds of thrust. So we're on the scale of a small satellite launch vehicle upper stage, and we're targeting 500 psi. In the last few months, we've been able to achieve detonation in the chamber. We're achieving ignition and detonation were very significant challenges at this scale. And we've been able to operate this at 50% power level, working currently on water cooling this to be able to go to the higher power levels. Our focus on this right now is improving the injector and improving the chamber wall survivability. So those are the two key things that we need to get the combustion right, and we need to get the cooling right in order to make this into an operatable system. Okay, let's go on to the next slide. Where does RDE fit in to this discussion? So going to slide 11 there. One of the benefits of rotating detonation, or even detonation combustion in general, is that it happens about 2 orders of magnitude faster than deflagration. So if when you approach the scramjet problem, you may be familiar with the analogy of it's like trying to light a match in a hurricane. There is an awful lot of air coming in at a very high speed, and somehow you have to get not only enough enthalpy to get your propellants ignited, but then also to flame hold with inside the combustion chamber. And so there are definitely a number of challenges here. With the detonation, applying a rotating detonation engine to a scramjet technology, there are a number of ways to do that. One of the options that kind of comes from an experiment done at Wright Pat, where you can see the image here on the right, has where they injected fuel into a cavity behind a rear-facing step and ignited that with a pulse detonator. And not only were they able to achieve ignition there, but they were able to have enough pressure release that it stopped the flow momentarily, causing a blockage there before the cycle began again, achieving ignition behind that rear-facing step. So that operates very similar to a rotating detonation engine. So currently looking to apply that same technology here. And again, there are a number of challenges. Getting ignition, getting detonation, and sustained operation are key, but that might be a way to allow to achieve scramjet operation and go into higher velocities.
Hey BJ, this is Rod. We need to wrap
okay.
up if you could. Thank you.
Sure. So slide 12. This is an experiment being conducted or being readied for Purdue next month rather, in Dr. Slaybaugh's group. They're working to test it up to Mach 4 conditions and work on the design of the inlet. How much do they have to slow the air down in order to make this operate? Of course, working on the injector, which is going to be key to it. And then varying what's really neat about Dr. Slaybaugh's experiment here, it varies the interior chamber body in order to see where choking can occur. Slide 13 is a set of, it's just a CAD model, but it's because it's easier to show than a messy test cell. This is one of the facilities at the Purdue High Pressure Combustion Lab, where they can do very significant levels of work at the 10 pounds per second level, Mach 4 relative flight conditions, 800 psi stagnation pressures. and adding a diffuser onto the back end of this will allow them to simulate 80,000 foot altitudes. And then in addition to this, the high pulse facility that Purdue's investing in, it was already mentioned, and that will allow some investigations, not necessarily in the propulsive field, but informing these designs in the Mach 7 to 10. And then slide 14, I just wanted to mention that there's the competition's already moving forward with this. The Russians have been working very actively in detonative combustion for over 15 years now, and Bykowski's work in 2006 was really a wake-up call where he was able to achieve some of these things that we're still working on our way to all this time later. France and China are still moving forward with designs, and Japan is getting into the game as well. So, okay, thank you very much for your time.
Thanks so much, BJ. So I just want to give a big thanks out to Carlo, Tom, David, and BJ for their talks. Again, as I hope everybody will agree, some very fascinating work going on for those of us who work and understand the Department of Defense hypersonic mission. This is all highly relevant. This work will drive the innovation required for us to have a hypersonic deterrent capability for the United States from a defensive and offensive capability. And I hope that nobody ignored the fact that there's also a lot of applications to space. So with that, I'm going to throw it back over to Dr. Kaiser. Over to you, Bill.
Great, thank you, Rod. I echo your comments. This is really these are great technologies. It's very impressive, and it should give us all faith in the research enterprise of the U.S. So there are no questions. So I still encourage you to shoot questions out across chat for these. Even if we don't get to them today, we'll make sure we answer them and send them out to all the attendees. So in the same spirit as hypersonics, Crane has a very strong expeditionary activity of the technologies that they concentrate on, certainly revolve around UAVs. So our next two presenters are from the UAV community. Our first one is Dan Bosch. He's the CEO of Sick Drone out of Boston, Massachusetts. Sick Drone is a veteran-owned Massachusetts-based small business. Their expertise is that of manufacture of high-performance drone systems. So I think it's a very fascinating technology. So kick it over to you, Dan, to talk about Sick Drone.
Hello, everybody. Hopefully you can hear me okay. I'm Dan Bosch, CEO of Sick Drone. We are the maker currently of small unmanned aircraft systems. So I'll get right into it and switch the slide. Can you hear me okay? We can switch the slide.
Yeah, we've got you, Dan, coming through loud and clear.
All right, thank you. So we're focused on high performance unmanned aerial systems. You can see right there our speed capability, and it's combined with thrust vectoring. So thrust vectoring mainly at lower speeds, lower than 100 miles per hour, you can see increased stability and maneuverability. As far as how hexacopters work, which is our platform, anybody's researched or been involved in aircraft in the past, you can rotate the aircraft body less if you can vector your thrust, and it's a pretty cool technology, especially in small drones. We are a 15-person small business founded in 2016, veteran-owned, Navy veteran. So excited about the possibility of working with the Navy. And we have our facility in Peabody, Mass, where we have a water jet, 3D printers, and a small production facility to accommodate what we're working on currently. We have DFARS compliant capability. We also are advanced in our secure transmission of data with AES 128-256, and also have jamming and anti-jamming capability on our aircraft. We are midway through our phase 2 SBIR contract with the Air Force, going along quite well, where we're focused on counter-UAS applications and Blue Force interceptor capability with a small drone system. Go ahead and change the slide. So our sponsors on this page and current customers, we started 2016. We were immediately chosen by Jaguar Land Rover for their technology incubator in Portland, Oregon. So we work with their special vehicle operations team along with the Red Cross to create a workable drone system to launch from Range Rovers, which is very fun. Went over to the UK and did demos with them. Still matched up with them, and they're waiting for us to get into production to possibly pursue small drone systems for search and rescue units. We are currently working with the Rapid Sustainment Office in the Air Force Manufacturing Olympics and with Vineyard Wind on an offshore project here in Massachusetts, mainly focusing on surveying for marine life and sea mammals as they build these newly constructed offshore wind farms for the first time here in the U.S. on a grand scale. So that's very exciting too. You can go to the next slide. And myself started out at the Navy as an aircraft mechanic, went on to work at Boeing and United Technologies as an aircraft designer. Mechanical engineering is my degree from UMass. Tom went to UMass as well, and he's worked on rotorcraft aircraft, pretty advanced rotorcraft aircraft, such as the built V-280 Valor, which is coming out soon, and a very high-tech advanced aircraft. It is replacing the B-22 Osprey. And Dennis Hernandez has almost 20 years of military experience as a Special Forces engineer, and he's helping us guide some pretty high level importance projects at the time. So please advance the slide. Here is our platform. Pictured there is our SIC-5 aircraft. It can reach speeds exceeding 100 miles an hour. It's about 4 feet in diameter, so larger SUAS system. Exceeds, right now it's hovering between 20 and 25 pounds total. So this tilt rotor system, so the right and left rotors rotate, allowing the center body to rotate less and the thrust vectoring to provide more useful power for the system, creating higher levels of efficiency at lower speeds, and then quicker acceleration to get to the higher speeds for interceptor type flight missions. This aircraft has a 5-pound payload capability. We are in work on our 25-pound payload aircraft, the SIC-25. Both aircraft have a hybrid power capability, so flights exceeding 2 hours, and also a LiPo powered with 30 minutes of flight. So integrated modular systems on all aircraft, which is exciting for our customers, that you can replace the lower system in a matter of minutes, slide in and slide off and slide on entirely new camera and sensor payload package. Also payload packages accommodating transportation of tools and goods for search and rescue. And as an example, in the past, we were transporting some specific to search and rescue packs and things of the like. So a lot of possibilities with our modular lower system. And we are obviously building them to aerospace grade quality levels. Both Tom and I are focused on this, utilizing our aerospace backgrounds to kind of bring small drones to another level of quality unseen to date. Next slide. So with these modular lower systems that we have, we can accommodate very quickly. In fact, beyond what we're focused on right now, which is counter SUAS, into various artificial intelligence packages, electronics signals packages, being nodes for communications. We're working with the Air Force now with their Ninja system to be an aerial communications node, for example, along with many other flight mission possibilities. So you name it, we can probably support it if you're looking for a hexacopter type platform for the mission. Next slide. And our product specs right here on this page, the main difference you can see is just LiPo versus hybrid powered. Our SIG-25 will be hybrid powered only, and our SIG-5 has the option of LiPo or hybrid power, along with the other specs that I've previously mentioned. Next slide. So this is an overview of our current status on our SBIR, where the Air Force is interested in our maneuvering and performance capability to provide security and to provide Blue Force counter UAS drone for multiple missions related to incoming drones, incoming security breaches, to be able to quickly deploy a drone to protect Air Force bases and Air Force assets immediately and convincingly as a Blue Force interceptor type platform. So our testing so far has been in Massachusetts and also Griffiths Air Force, Griffiths International Airport in Rome, New York, where we have a wide, it's a very big, large facility where we can do any number of tests relating to interception, relating to long distance runs, related to comms checks, related to everything to provide adequate security and what the Air Force is looking for with our platform. Next slide. So this is kind of a timeline overall for the company. Initially selected for the incubator with Jaguar. From there, we had a drone developed that we traveled speeds between 80 and 90 miles an hour top end. It was a smaller system than we have today. Moved on, selected by Techstars and the Air Force for our SBIR. And now we have aircraft exceeding 100 miles per hour in the Group 2 and eventually Group 3 platform weight categories. We'll be in the Group 3 for our SIG-25. We're in the Group 2 UAS for our SIG-5. That's 20 to 55 pounds. And delivery is set for 2021. At the end of conclusion of our phase 2, we have to deliver 5 SIG-5 hybrid platforms to the Air Force. And we would begin low rate production in 2021 as well. That would coincide with delivery to Jaguar and delivery to Vineyard Wind and other current customers. So we're excited for that. Just north of Boston, our facility right now can handle about a dozen or so drone units per month maximum. We're moving across the street to a larger 30,000 square foot production facility where we can handle a little bit more than that per month. That is also an exciting change for our company and one we're looking forward to. Next slide. So here is a couple of pictures, mainly from our flight tests in Rome, New York. We have a video. I don't know if you guys can have the capability to play that during this slide. It was sent as a separate file.
Sorry, I do not have the video ready to go right now.
That's all right. The picture should be good enough just to kind of give you a general idea of the size and look of our SIG-5 aircraft. This is the LiPo-powered prototype version for the U.S. Air Force. And we imagine that whether we're working with Special Forces, Navy, the energy companies that we're working with, it looks very similar to this platform. The lower system would just look different based on the camera and sensor package that you have. We can go to the next slide. So in summary, the slide's just taking a little bit longer to change on my screen. We're looking to form relationships beyond the Air Force. So we're excited about the possibility of working with the Navy, Special Forces, and the Army, as the Army has been designated the official leader for counter-UAS operations for the entire military. So as we expand and get further and deliver these very capable aircraft to the Air Force, we want to be able to start going and traveling. I mean, with COVID, it's harder to do these demonstrations, but get in front of the Navy and get to your facilities out there in Indiana. That would be very exciting for us to do some flights and demonstrations out there for you, for your group that's on the call today, or for other groups that are interested in high performance small drone systems. And next slide. And that wraps it up for us today. Thank you for letting us speak today. We're looking forward to the potential partnership with Naval X and IN3.
That was great, Dan. Thank you. It sounds like a pretty interesting drone. And certainly anybody who puts a picture of the Navy Law system in their presentation is a hero of mine, right? It's a great counter system. So our next presenter is Rob Hetler, the Director of Applied Development, and Craig Williams, the Director of Integration and Operations at Asymmetric Technologies from Dublin, Ohio. They're going to talk about their Ironclad Secure Flight Controller. It's an American-made open architecture flight controller for unmanned aerial systems that is built from the ground up with embedded cybersecurity features and edge computing capabilities. So Rob and Craig, take it away.
Okay, thanks, Bill. Let me know if I have any audio or video issues here. Next slide, please. So we wanted to lead off with just a little bit about Asymmetric. We're a service-disabled, veteran-owned small business in Columbus, just a couple hours from Crane. Our founder, Brian Borkowski, and current owner, he was in the Army for about 17 years as a combat engineer. And one of his last assignments was at an Army research lab, and that inspired him, I'll say, to start his own business and try to do the tech transition part of things a little bit better. And so that's where Asymmetric was founded in 2011. We're up to about 35 people at this point, and just moved into a brand new 18,000 square foot office and lab space. We moved just in time to all be told that we're going to work from home for a couple months, but we're starting to filter back into the office now. We do have a commercial UAS division that does infrastructure inspection and other service type applications. So that gives us a couple nice things. That division was actually acquired by Caterpillar for a couple years, and then it came back under our fold. It's a long story, but essentially it gives us access to pilots, testing capabilities that we might not otherwise have. And is a good part of the team here. Our team is the engineering R&D, side of the house. The applied development team, we have electrical, mechanical, software engineers, and some program managers. That's where Craig and I sit. And then we work real closely with the Ohio State University for the hardcore aerospace application type stuff, and have a really good relationship over there. Next slide, please. So a little bit of background. When we talk about flight controllers, sometimes I jump right into this and people don't necessarily understand what the flight controller, otherwise known as an autopilot, is. Every drone, every UAS that's out there has a flight controller on it. It has avionics sensors that help the drone know where and how it's positioned in space. It runs the flight control algorithms on some computing processing capabilities on board. It has IOs for things like GPS and payloads, and it's really becoming the central computing hub of any drone, any UAS that's out there. So you see some of the headlines that I pulled here just from recent headlines, and I'm sure everybody on this call is aware of the concerns and the issues around cybersecurity. And 99% of the requirements that I see for UAS in the cybersecurity section, they list an encrypted radio link. And what I always like to say is that's very similar to saying, well, I'm going to put, excuse me, I'm losing my voice here. I'm going to encrypt my Wi-Fi on my laptop, but if you accidentally leave your laptop at the coffee store and there's no password on it, that's a pretty big issue if somebody gets a hold of it. So we've looked at this and decided that there was a gap in the market here. Typically at the low end, you have Pixhawk type flight controllers, which are great little flight controllers, but they're typically made in China. They have zero cybersecurity implementations on them. And then you move all the way up to proprietary systems, which are very expensive. Again, though, have very few cybersecurity features and cost a ton of money and are not an open architecture where you can go in and change things. Next slide, please. So to approach this gap, we started about 3 years ago developing what we now call the Ironclad Flight Controller. And we built this from the ground up with the idea that we're going to use open source flight control software, a couple examples of which are shown there on the left, and couple it with a board that we built from the ground up, our CTO designed from scratch, that has cybersecurity features kind of baked into it, along with very high-end computational capabilities. So what this gives you is this platform agnostic, open architecture, control and communications capability. And you see a couple of the platforms there that we're integrating onto as we speak. Next slide, please. So a little bit more on the details here. Of course, this is American made, American manufactured, and so it addresses a lot of the concerns with Chinese made components that are running rampant in DoD right now. I mentioned we couple it with controlled versions of open source autopilot software. And that's an important distinction, is that we're not asking people to go out and download the latest version of PX4 off of GitHub and use it. We're packaging that in a application specific way for DoD. We have a very high-end edge computing capability on board that's, I'll say, integrated a little bit deeper than a lot of the flight controllers you'll see out there. And that's primarily for cybersecurity reasons. But the security features run the gamut of any really highly secure piece of hardware. Without going into a ton of details, contact me if you want some more of those details. But essentially what you end up with is a flight controller that you can use commonly across any drone that's out there without having vendor lock on the flight control software, and have assurance that you're in a secure environment. We've also, for some of our projects, integrated with ATAC. And again, I can give people more details if you have interest there. Next slide, please. So here's how we envision this rolling out. And this is actually, I'll talk real quickly about a couple of our programs, but this is how we see the world. And there's an important distinction to make here. A lot of times people talk about common ground controllers and kind of confuse that with the same capabilities that we're talking about here. An example is, a common ground controller is really just translating message traffic that's coming from proprietary systems on the drones themselves. So the inherent capabilities of those drones doesn't necessarily change. For example, there's a very popular, I'll say, DoD platform out there right now that it can only do 4 waypoints on a mission, which is really kind of out of date, not kind of out of date, it's completely out of date. You can use a common ground control station with it, but it doesn't help you get any more waypoints that you can hit on a mission mode flight. You really need to change out the flight controller and the flight control software to be able to do that. So we see this, if there's a common flight controller, hopefully ironclad, but whatever it is, across multiple platforms, it really gives the operator common training, common logistics, common capability sets that they're familiar with, instead of just translating message traffic on a common ground controller, which is the approach that you see some of the services taking. Next slide, please. I talked a little bit about this already, but the idea on the software side is to specify, package, validate, and create assured software modules. And as new features roll out from the open source community, we would test and integrate those, at specified intervals with configuration managed software packages. And the same on the ground control software side. We're actually knee deep right now in modifying Q ground control for some SOCOM applications to make it a little more relevant to what those guys are doing. Next slide, please. So of course, we first did this for a program called the Silicon Valley Innovation Program out of DHS, starting in about 2017, early 2017. And it's kind of coincided with the rise of concerns about foreign-made components, Chinese-made components. So we're getting a lot of interest right now from government clients, and you see some of them listed here along with the funding clients there on the far left. We've received significant support and tracking from the clients there in the middle. And then you see how we plan to commercialize this, which is essentially we're going to sell it direct to manufacturers, to a company like Sick Drone that was just on there. We haven't talked to those guys, but they could potentially put Ironclad into their system and use probably the exact same software they're using now. And then we're going to sell standalone controllers so people can buy them and do whatever they want with them. And then we continually innovate and put new capabilities on board as time goes on with both internal and government funding. Next slide, please. So a little bit about some of the programs we're working right now. This was the Silicon Valley program I just mentioned. We've been through 4 phases of this now. Just wrapping up the 4th phase, which is technically what's allowed under the program. We're talking about potentially some follow-on work with DHS. But essentially, this is the program where we built the first prototype, flew the first time, and now we're doing operational kind of testing with them. You see some of the environments that we've flown in out in the San Diego area over the past about 3 years with DHS. They've been a great client. Next slide, please. Ironically, very similar to Sick Drone, I believe they were funded under the same Air Force SBIR that we were, the SUAS pitch day. We likewise are about 1/3 of the way through our phase 2, and the scope of that phase 2 is kind of what our dream for this is to replace the existing avionics on 3 operational platforms for SOCOM, put the Ironclad in and show them some of the benefits of a common secure flight controller across those 3 platforms. So we have those platforms in our lab now. We're in the process of modifying them. And I wanted to pull this slide this graphic real fast just to show that the stepwise risk-reduced process that we follow that includes, we have hardware in the loop simulation capabilities with the Ironclad. So on one of the platforms that we're working on this project, we built the flight control algorithms in simulation, went out and flew with them for the first time a couple weeks ago, and they worked almost flawlessly. And we're not naive enough to think that that's always going to work, but it gives you a really nice starting place before you put your flight controller on a several $100,000 aircraft and keep your fingers crossed that you don't drive it into the ground. So that's the process that we follow there. Next slide, please. And this is another exciting project we're working right now. This one's actually State of Ohio funding through a program called Soaring from the Ohio Federal Research Network. And this one, we're doing something a little bit different in that we're working with Ohio State and Ohio University and Lockheed to build 3 new capabilities onto the ironclad. The first are some advanced control algorithms to make the aircraft a little more fault and damage tolerant. So if you damage a control surface or a prop, the control algorithms can account for that and try to readjust themselves if they can to try to save the aircraft. The second capability is built around an open source autonomy algorithm that came out of AFRL, and it basically gives you a sensor agnostic intelligent scheme to help how to decide to deal with conflicted airspace and formation flying, things like that. And then the third is more on the cybersecurity side, and it's integrating something called a physically unclonable function module for even higher end cybersecurity. And at the end of this program, we're working with Lockheed Martin RMS to put the Ironclad onto one of their platforms. It's called the Condor. And then we're going to go demo each of these capabilities over at Wright Pat to show how all this works together. Next slide. So in conclusion, we feel like we kind of lucked out with our timing on this. We have a cyber secure, open architecture, flight control capability, and the challenging part is there's a lot of OEMs and long-term DoD vendors on the UAS side, I'll say, that say that only their flight controller can fly their platform, and I quite frankly call BS on that. But there's a lot of entrenched interests, and so that's the challenging part for us, is convincing people that this makes sense. It saves the government money, it saves training, it's safer. All of these things, but long term, we'll see where it goes. But we're excited to work with the Navy. We did have an ONR SIBR that we just finished up, but we're looking for other opportunities to put this on people's platforms and see if we can do good stuff for them. So that's it for me.
So that was great. Thank you very much. And I'll open it back up to the audience again. I'm not seeing any questions in the chat. So I'll open up the audience here for a minute or so to see if they have any questions. And if no one chimes in, I'm going to ask a question or two about the flight controller, and then also about the sick drone if we still have Dan on the line. All right, Rob. So some questions about the Ironclad. Now, does it have the initial navigation system? Is that something you guys built custom? What sort of accuracy does it have? And then another question I have is, can you get an output from that INS to operate or provide data to payloads?
So yeah. The answer to both questions is yes. The board has redundant IMUs on board. I'll say we tried to pick the upper end of sensor technology, and again, we work with Ohio State pretty closely on that at the outset. And yes, we can output that data to payload packages or whatever other onboard applications you have. So the answer is yes to both of those.
So to some extent, you've taken the step to remove some of the stovepipes in the architecture for UAVs, right? You're trying to have some level of common electronics between payloads and flight controllers. Is that right?
Yeah, you're absolutely right. And I didn't talk about it a lot, but one of the things we saw when we started working drones at Asymmetric is everybody we met that was doing something cool with drones had a Pixhawk, and then they had 1 or 2 Raspberry Pis strapped to their aircraft. And our CTO said, that's kind of dumb. We can do this all with one integrated processor. So we kind of segregate the flight control software on the one little portion of the overall processing capability. And then we leave the rest to the user. So that can be autonomy functions, that can be video processing, that can be pretty much anything you can think of.
Now, is that extensible too? I mean, are you able to add extra modules to that as required?
We can, yeah, that's a good question. We actually have an expansion port on board. And so, for example, you know, if you have a very specific GPU that you would that you've already built your software, your application around, we can plug that directly into the expansion port if it, you know, if we can't handle it with the onboard processing that we have.
So what is that communication protocol or that expansion port?
So it's got it's on our spec sheet that I could send you. It's probably got about 10 different IOs in the expansion port. So pretty much anything you could think of, Ethernet, SPI, CAN bus, all that stuff is available in that. But we also have IOs that are kind of standalone IOs around each of those as well.
Excellent. Do you have relationships with a payload manufacturer or multiple payload manufacturers?
Yes and no. I don't think we're in real deep with any specific payload manufacturers. We've been more focused on the UAS platform side and getting a toehold there, if that makes sense. But you know, we've integrated several different payloads over time, but you know, the focus up until about a year ago was just getting up and flying safely and trying to troubleshoot, you know, since we're only about 3 years into this.
Great, thank you.
Yep.
Any other questions for Rob or the UAV team? Well, I'm gonna take a minute or two more airtime and then go back to Dan and ask about the types of payloads that they've flown on Sick Drone, and if they have a roadmap for the different types of payloads they're going to fly, and have they ever thought about swarm technology on that platform? Dan, have I lost you?
Oh, no, I thought you were leaving a couple minutes open there. Sorry. I'm here. So as far as the payloads that we have flown with, we've flown with a number of different cameras. We've flown with different LiDAR configurations. So we currently have like downward facing LiDAR for altimeter purposes, and then forward facing LiDAR for sense and avoid. And now we're getting into where we will do some sensor fusion for as far as detect and avoid capability using 3D cameras, LiDAR, and radar. So as far as the requirements for the Air Force, we have to go by what they're suggesting to us, and then we also have to go along with our current plan for, you know, just a capable overall drone system. But what wasn't clearly shown in the presentation maybe was just how the modular lower platform works. Right now, our current design that will be our first production design comes with a rail system where you can slide off the lower system and slide on it entirely new. So that being said, the lower system includes if you're using the battery powered system, it includes the LiPo batteries, along with the LiDAR sensors, along with the gimbal and camera system that you're requiring to use. Now the gimbal can fit 2 cameras on it at a time. Our system provides for up to 3 cameras in use. So what we've done so far, we've only used 1 camera at a time. In the near future, we'll be trying lower payload packages that include 2 and 3 cameras working at the same time and transmitting long distances. Since we're in the Boston area and we're working with Vineyard Wind, we'll be going beyond land-based tests. We'll be doing some ocean over ocean and coastal testing. So that'll be cool to see how well our video and telemetry data transfers out to these wind farms that we'll be working with. So a lot of cool things in our future, and you know we've had in mind for a while a modular system down below that can be customized. So if a customer such as the Navy, for example, needed a a differently configured system than the Air Force, we could accommodate that pretty quickly. We're using rapid prototyping, rapid manufacturing techniques. We have a water jet machine and Mark forged carbon fiber 3D printers in-house. So within 3 weeks, we could have entirely new modular lower system that accommodates the custom needs for various branches of the military and you know, into our commercial customers' needs.
That's great. Thank you. So I don't see any more questions. Naval X team is incredibly appreciative of everybody's time today. I hope we're able to exchange information that the companies and Crane find of interest, that this leads to further conversations and more importantly for the companies, you know, opportunities to move their technology into other branches and other applications. This will be online. If you need contact information or further information, feel free to reach out to the Naval X team, and we'll gladly provide that to you. So I think we'll give back 6 minutes of everyone's day today. Once again, I thank you very much and look forward to engaging you on future events. Thank you.